In this lecture, we're going to look at some sort of miscellaneous last-minute topics related to chirality and stereochemistry before moving on to some newer topics. I guess the next two lectures have a little bit have some miscellaneous topics related to stereochemistry. It's a big field. Okay, so just a second, I lost control of my mouse. Okay, there we go. So getting into it. Right away, what I want to do is introduce some new terms. One, and they're both related to sort of configuration. So this is other terms in stereochemistry. Now, they are absolute, and I'm going to leave some space, and relative configuration. Okay, so absolute and relative configuration are two important sort of sets of words for describing the stereochemistry of chiral molecules. And we've been actually studying absolute configuration for a few lectures now. This is the R or S assignment at a stereocenter in a molecule. And that molecule needs to be chiral. So if I gave you this molecule, we would say the absolute configuration of this molecule at its lone stereocenter is, well, let's see, 1, 2, 3. It looks like we're going counterclockwise, is S. So the absolute configuration of a molecule is merely the RS assignment. This is something that we've been looking at. So this is just, by saying absolute configuration, we're helping us to, it's just an easier way of asking, what's the RS assignment at any particular stereocenter. Notice that for us to determine the absolute configuration, the three-dimensional nature of a molecule must be explicitly defined. So if I just draw a molecule where there's a stereocenter, and we have a chiral molecule, but I don't indicate what the three-dimensional arrangement is, by forgetting to draw the wedge or the dash, the molecule is still chiral. It still has a stereocenter, but the absolute configuration is not available. So we cannot kind of or not applicable. So we can't say what the absolute configuration is, because we can prioritize the groups, but we can't make sure that number 4 is in back because we don't know where number 4 is. The hydrogen that's implicitly drawn in these molecules, if I don't define a wedge on the bromine, then the hydrogen, I don't really know. It could be in front, it could be in back. So writing RS would be a 50-50 shot, and that's not helpful. Okay, so we need wedges and dashes to determine the absolute configuration. Now the relative configuration, this starts out a little bit more vague, but it actually ends up being somewhat more tractable and easier to grasp than the absolute configuration, just because you don't have to work as hard, you don't have to prioritize things as often to determine the relative configuration. But this is a description, excuse me, of the relative orientation, or just, I could write the orientation to keep defined words out of our definition, a description of the orientation of stereocenters relative to each other. I guess I do need that word relative in here. Relative to each other. And I find this was a little bit easier to grasp. Instead of R or S, we're going to use the labels cis or trans. So not RS. Instead, we're going to use cis/trans. Now, when we say cis, we mean the groups are on the same side of the molecule. whereas trans, the groups are on opposite sides of the molecule. Okay, so cis and trans, they're used actually quite a bit in fatty acid chemistry and fatty acid description. And so many times you will have heard the term trans in the context of something related to chemistry when you're talking about trans fats and that sort of thing. We'll talk about those later on in the semester, but it's actually not related here. So it turns out that the best time to use the cis or trans label is when you're describing a chiral ring structure, a chiral ringed molecule. So best time is when you're dealing with a ring structure. Okay. So what I'm saying is, let's imagine we've got some ring structures where we've got two cyclohexanes. Now in one cyclohexane, we've got two wedges. In another one, we have a wedge and a dash. What I would say about the one on the left is that the two groups, and the groups are the methyl groups, are on the same side. Maybe you want to say the same face, as though it has two faces or something. The same side / face of the molecule. Either way, they're both up, and they're both, relatively speaking, pointing in the same direction. So they're both pointing up or towards us. Alternatively, in the other example, we have the two groups are on opposite faces. And they are each pointing in different directions. In the case of the two groups pointing towards us, we would say that relatively speaking, they're on the same side, same face, or the cis, or having the cis relative configuration. Relatively speaking, they're on the same side. They're cis to each other. So cis, relative configuration. And then using this in a sentence, we would say, I really like this latter point. Calling something cis works a lot of the time. Just calling a molecule cis works a lot of the time when it's appropriate, or trans conversely. But what generally is more useful is to say the methyl groups are cis to each other. Now, if you're following along, we would say that in the right example, we have things moving in the opposite direction. That is the trans relative configuration. Where we would say the methyl groups are trans to each other, which I prefer that approach. Okay, so this is relative configuration, where we have a ring structure with wedges and dashes, and then we look to see how are the stereocenters kind of oriented with each other. If we have two groups, and each of the, on our ring system, only two groups at stereocenters, and the other the stereocenters only have one non-ring substituent, that is, they've got the ring, the hydrogen in a group, then we can call the overall molecule cis or trans, depending on the arrangement of the groups. However, outside of that, it's a lot better to say that the methyl groups are cis to each other, or they are trans to each other. Okay, so that is to say, if I had to summarize, when labeling cis/trans, focus only on two groups at a time. Okay, so if I had, let's pick another example. Let's say we've got a four-membered ring. We've got A, B, and D. And so I have wedges and dashes written in this arrangement. And what I would say is that since A is a wedge and B is a dash, I would say that A is trans to B, or A and B are trans to each other. So A is trans to B, A is cis to D, because in the case of D and A, they're both wedges, they're both pointing on the same face, and then B is trans to D. Okay, now in this case, we have three stereocenters. So we have to focus on two if we're going to give the overall molecule this label of cis or trans. So in this above example, I cannot label the overall molecule as cis or trans. So I can't say that's like a cis cyclobutane or a trans cyclobutane. It's got multiple stereocenters. So if I labeled it cis, you might be like, well, you can label it cis, like A and D are cis to each other, but A and B are trans to each other. And so that's where it's more helpful to indicate cis and trans, is to say like A and B are cis to each other, A and D are cis to each other, A and B are trans to each other. But if we only have two substituents, then IUPAC says, hey, go ahead, use the indicator cis and trans. All right. An example of that would be right here. So in this case, we would call this cis 1,2-dimethyl cyclohexane. Okay, that's an IUPAC name. That's actually a very helpful name because it differentiates us from the trans isomer. So that is the trans 1,2-dimethyl cyclohexane. And you might be like, well, okay, it's kind of, it makes sense. The cis and trans makes sense. It's kind of weird that, like, sometimes you can use the you can kind of write the name of the molecule, but with cis and trans, but not always. Like if you have multiple stereocenters. Well, it turns out that what I've got written on a piece of paper right now is also not a great name. That is, by writing trans, it's not a great IUPAC name because remember when we were talking about naming molecules, we said we wanted one name to correspond to one molecule. So when I write an IUPAC name, that should correspond to one molecule. Well, if we don't have R and S included in the name, then maybe one name could correspond to a few enantiomers. Well, that's true, but we can add stereochemistry prefixes. We'll see as we get into naming haloalkanes that if let's say we've got a stereocenter at the 2 position, we could just write 2R in front of the entire name. And that indicates to us that at that second position, we have the R absolute configuration. And then we know if we have a wedge or a dash based on how we drew the molecule. So even though we haven't included stereochemical descriptors in our names thus far, like in exam 2, I didn't ask you to do that. But even though we didn't have that, doesn't mean we can't. Actually, maybe a few of those molecules I gave you were chiral. We'd have to go back and look. But if I don't include the stereochemical descriptors, then we just don't know the wedges and dashes. But in this case, we do. In this molecule I've drawn, I've shown you the wedges and dashes for the trans isomer. They're going in opposite directions, so you labeled it trans. But I said this isn't a great name because it includes a stereochemical descriptor and it describes multiple molecules. Now, multiple molecules, what do you mean? Highlighter off. It could mean one of these two molecules. Well, those two molecules are the same. The methyl groups are attached to a cyclohexanes going in opposite directions. They're similar, but similar is not the same. These two molecules are, in fact, enantiomers of each other. If you look at the molecules, we flipped the wedge and the dash in both cases. So these things are actually enantiomers. So, for example, this looks to be R. This looks to be 1. This looks to be R, and over here is S and S. So we have the RRSS version of the molecule, and we could include that in the name. I don't want to get into it right now. I don't want you to worry about it. But so we've got one name that corresponds to these two molecules, and I said that's an issue. It might just be easier to say the two methyl groups are trans to each other. Now, what about this first example, the cis example, where I labeled all of this, and I said that's a pretty good IUPAC name. You might be like, well, doesn't that also describe this molecule? Well, actually, in both of these molecules, I mean, while you'd like to say that because we could draw the enantiomer and be like, hey, these two structures right here and right here are different from each other, right? So if they're different from each other, then that cis name corresponds to both of them. Well, in this case, it doesn't because both of these are achiral, and the technical term is they're meso. They've got stereocenters, but they have a bilateral plane of symmetry through the molecules so that we know they must be achiral. Achiral, despite having stereocenters, is the definition of meso. So when you have the cis isomer, the cis diastereomer, the difference between cis and trans are diastereomers. The cis diastereoisomer up above is meso. So cis describes only one molecule. Whereas the trans, I should include my R in here. The trans diastereomer is chiral. And so trans describes two molecules. Now that's just in this one example. Cis and trans could describe meso molecules or chiral molecules in other cases too. So for example, this is a cis molecule, but now it's chiral. Similarly, if I had this molecule, this looks like our dimethyl compound from before. It just happens to be in a 4-membered ring instead of a 6-membered ring, but now it has a bilateral plane of symmetry, and we say that this trans molecule is achiral. So cis and trans can describe overall achiral molecules. They're just trying to point us towards the relative orientation of two groups on a ring system. And so there are some rules about when you can use them. But let's go ahead and practice this. What I want you to do is be able to look at a molecule, and if I said, okay, the two stereocenters, or the two groups drawn as wedges and dashes, Are they cis to each other or trans to each other? Let's look at some examples. So apply the label cis/trans to the di-substituted molecules below. Okay, so from a 6-membered ring to a 5-membered ring to a 4-membered ring to a 3-membered ring to a benzene to a butane chain. Okay, so in the first case, we have a ring structure where the groups are moving in opposite directions, so those are trans to each other. Second example, both of the methyl groups are pointing up or in the same direction, and that's cis. I'm also going to make note of it that this molecule happens to be meso. The next molecule, we're at trans, and lastly, we're actually at not applicable in this case. It's not because the molecule is not chiral, but the groups are on the same carbon. So it's not necessary. I mean, if there's a cis isomer that you can label, you should be able to draw a trans isomer, and there is no second kind of isomer for this molecule. So it's not helpful to draw cis or trans. In this next example, we have a benzene ring. The molecule is entirely flat. There's no three-dimensional component that's provided because none exists. You can draw the entire molecule as being parallel to a piece of paper. Now, the last molecule is also not applicable for cis or trans, and that's because it's not a ring. I know those groups are moving in opposite directions as I have them labeled, but you can't label this trans because you could do free rotation and make it so that instead of one being back and one being forward, you could do free rotation to make them both forward. And the cis or trans should be specific for the structure that we're looking at. And so I think that should do it for kind of relative configuration. So with relative configuration, we want to look at molecules, and particularly di-substituted molecules, and label the molecule as cis or trans. Notice that in some cases it's not applicable. Additionally, what's probably more helpful is to just look at two groups on a ring. Maybe the ring has multiple groups, and we say those groups are trans to each other or cis to each other. And then if we, with enough time, we'll get good at using this terminology for cis or trans. Okay, but that'll do it for this lecture. In the next lecture, we'll move on to some of the last topics related to stereochemistry.